Bhavik will start.
Yeah,
Ju-
let me start
ju-
sharing.
Just a minute, just a minute, just a
Yeah,
minute.
okay.
Good morning, everybody. So we start our day 5. So we have with us Mr. Bhavik from Cisco, Bangalore, India. I request Dr. Rafida, Assistant Professor, Department of Computer Application, to introduce our speaker.
Good morning, all. A brief profile of Mr. Bhavik Shah. Bhavik Shah currently works in Cisco Security TAC and assists in security deployment in large enterprise networks. He has delivered training on IoT hacking in Null Bangalore and also OVAST Seaside. His interest lies in IoT and digital forensics and also delivered a talk on network forensics in Null. He has also conducted the first CTA for Cisco by contributing challenges on reversing and binary exploitation. He has been a speaker for different universities like SSN, TAPAR, by delivering talks on IoT and application security. We, on behalf of Department of Computer Application, welcome you, sir, for the session. Sir, please.
Sure. Thanks a lot, ma'am. Let me first share my screen. Oh, Zoom needs, just a minute. Zoom needs permission. Interesting. Can you see my screen? No, right?
No.
Okay. Yeah, I need to give permissions. Interesting. Okay. I would be rejoining. I'm just given the permissions, Zoom to record my screen. So I would be rejoining. Sorry.
Sure.
Perfect. Apologies for a few delay, but yeah, okay. That is, sometimes it happens in remote session. So good morning, everyone. Thanks a lot, Vinod sir, for giving this opportunity. So today we would be talking on reversing essentials, right? Now, as you see here, it's the reason I mentioned is a refresher is because considering 90 minutes, I believe you would also agree that it's impossible to cover everything, the nonsense of reversing, what are the techniques and what are the concepts. It's impossible to cover in 90 minutes. So that's the reason what I've done is I've just broken into few parts. Like this is a basic one. Again, it's not that basic, but at least it would give you some ammunition to start, right? And what to look for, and hopefully post COVID, or maybe I would be really grateful to have more in-depth sessions. I mean, that's how I've designed this, right? So that's it. So that's the reason I mentioned as a refresher for many more in-depth sessions to come, right? Talking about myself, as ma'am mentioned that I'm a security consultant in Cisco, where we work on different enterprise deployments. But apart from that, I'm a cybersecurity enthusiast where I am keen on learning new stuff, exploring new security fields or domains, and not exactly trying to find vulnerabilities, but trying to find how the system works and what to look for, and how to identify that there are security loopholes. And that's how you identify it, and that's where I started my journey from a small home router which we use for our CCTV cameras, and then found the vulnerability in it. And yeah, I mean, and what I understood from that is basically, if you look for cheap products, you also compensate for the security in that, right? So that was the biggest learning in me, what I got while working on that. And as I mentioned, that I keep on learning new stuff. Now, the other thing which I'm currently focusing on is the cloud thing, because cloud is something which is booming everywhere, right? And everyone is trying to get hands-on and trying to understand what it is. And we in Cisco, I along with two other folks are working on some interesting project. I'm sure. Once it is ready, I'm sure Vinod sir, you would be the first one I would be letting you know. But it's something interesting. I cannot reveal much because it's not yet ready. But we are going to launch in SecCon this year in the month of November, and I'm sure all the participants, at least who does not know the cloud skills, or at least who knows the cloud skill, would enjoy it. Just to give a few insight, it's something to do with challenges. There would be different challenges in the cloud form in one of the cloud providers, and while working on those challenges, which would test your defensive techniques, and also at the same time you would learn different cloud nonsense. So that's the idea. Okay, and that's my Twitter handle. So I would really appreciate, or if you need to connect, we can always do it on Twitter. Though I don't advertise more on Twitter, but that is something which I got, something which I got maybe a recommendation from one of my peers to do that more often, so that people know that what you're working on. So that is something which I've taken as a point for myself to improve. Right? So that's it. Okay, so what's the agenda for today, right? So I would just briefly talk about what's the reversing process again. I don't see that as a rule where you need to follow this procedure, and this is a rule book which you need to be doing. I absolutely don't agree to that. It's something which I have been doing, and it's something which I experienced, that this is the basic flow which one should be going for. But again, each challenge, each problem, each binary is different. So you may have different approaches. So don't count me that this is the basic approach for all the binaries for which you need to reverse, right? So again, it's an individual experience, and you learn by doing more, right? So that's what I'm also doing. I'm evolving each day, and for now, whatever I learned, that's what I'm sharing you, right? The other, we would be focusing on what's a binary structure. The third is most importantly assembly fundamentals, right? Because when I started reversing, I had that fear that I don't know that much assembly. Would I be able to do reversing? And while doing that, I understood that okay, even if you're not good at assembly, you can still do the basic instructions. You can still determine, the normal x86 instruction set, and just because it's something which we have done during our engineering days, right? Yes, we didn't focus more on that. Yes, I'm not saying that everyone would not have focused, but and at least folks who are in electronics domain would have focused more. But then uh, as the days pass by, we tend to forget, right? So that's what I understood, that having the core assembly fundamentals, even if you don't have, you can still catch up with it, right? You can still go to the Google. You can still search for the basic x86 instruction sheet, and then determine what each instruction does, right? And then when you do, as you would see that when you do in a debugging console, you can still determine that what values are being passed and why it is passed, right? Because determining that relation is more important than just learning what move A comma B does, right? So that's what I understood. And last but not the least, very important, tools for binary analysis, right? Because nowadays, without tools, when I say tools, it's not something an automated tool which would give you the answer, right? But it's a tool where at least from say 10 pointers, at least it would give you 2 or 3 pointers, so that you only have to focus on the 7 important pointers where you need to find the relations and understand what the binary is doing, right? So tools are very important, and we would see today one of the tool. And just to spill the beans, it's not IDA, right? Because I just wanted to make sure that IDA is something which everyone uses, right? And I'm not saying that I won't cover it, but at least for this session, I will be covering some other interesting tool which is free of cost, right? So that is one thing. And last but not the least, hands-on. Again, considering the constraint of time, I don't expect every one of us, or generally what I do is I share the VM OVA file and you deploy, and then I give some time for you folks to work on it, and then we look at the solutions. But considering the constraint of time, I would just go through all the 5 challenges which I've built, right? And then understand that how to go about the reversing process. Okay, so the first important thing, right? Before we start reversing, why do we need it, right? Now, and I mean, why is it important? Now, if I consider my experience, right? As I mentioned, that I started with IoT hacking, where I just took a small home router, and started. I was not doing anything on reversing because I didn't knew anything about reversing. I'm not that good in coding, right? Because during my engineering days, I was always more interested in maybe the assembly stuff, but not exactly the coding stuff, right? Because I don't consider myself a good coder. So that was one of the reasons for me to get fear from reversing. I mean, I always used to ask question to myself that if you don't know coding, how you are going to solve the challenges, right? Because you need to, even if the tools would give you 20-30% of what is happening, but you still need to connect the dots and understand what is happening, right? But then from a business standpoint, or maybe from a career perspective, why do you need reversing, right? I mean, why there is a boom for people to understand, or to have reversing specialists to understand what is happening, is because once a system is being built, you need to understand that whether the system is being built is resilient or not. Are there any vulnerabilities, or basically are there any backdoor entries which you can exploit and do some kind of data exfiltration from that system, right? Because previously what used to happen is, once a system is being built, everyone used to assume that the system is foolproof. No one used to question, or no one used to basically spend time on the testing. I mean, ideally, when a system is being built, there is a testing phase. I mean, there is an agile methodology which is being in place, where testing scenarios are being done to understand that the system is resilient enough. But again, you still miss out something, right? And that's what the exploiters tend to exploit, in order to identify what exactly is wrong with the system. Now, in order to understand if the system is behaving correctly or not, you need to load the binary somewhere, right? Because the developer or the author of that system is not going to give you the source file, right? Because if it gives you the source file, then everything is so simple, right? So it's going to give you a binary, right? And a binary is nothing but an executable, which we use in Windows, and maybe in Linux it would be ELF binaries, right? So that exe is just a compilation of the logic which went in place, right? And that exe would be in the machine language, would be in the assembly language, right? And in order to understand that, you need to know, in order to understand how the system behaves, you need to know the concepts, how to and I mean, how to connect the dots and understand what the system is doing, right? And at the end of the day, if you're lucky enough, you basically file vulnerabilities, and that's how you make a name of yourself, right? I'm not saying that only finding vulnerabilities you make a name of yourself, but even if you determine, or even if while as part of your project, while you understand different systems, and even if you find a common pattern or the experience which you gained while doing that, and if you share, that is also a big thing, right? So that's one of the reason why reversing is one of the primary skills which everyone is looking for, right? And as I mentioned, that while doing the reversing, you also need to know what is the device supposed to do, because generally, if you are part of a project, or if you work for a company like Cisco, and say, for example, you have a project, at that point of time, yes, the customer would give you some insights of how the device is supposed to behave, right? And then while you do the reversing, you basically determine if the system is vulnerable, you basically determine some differences where the customer told you that, say for example, the device is supposed to blink green light when someone gives an input, say ABC. But while you do the reversing, you identify that if you give an input of DEF, it still blinks green light, which is a kind of vulnerability, right? So that is another important point of doing the reversing, to understand how the device is exactly supposed to behave. And as I mentioned, you want to make sure that all the device level protections are correctly being applied. You don't find any backdoors. You make sure that the device is resilient enough to handle any attacks. And last but not the least, you need to understand, as I mentioned, that you need to make sure that the device is supposed to behave the way it was, right? Not as what the attacker wants it to behave, right? That's the fundamental in any cybersecurity space, right? If you have built a system, it should be resilient enough from any attacks. And if it is not, then it means you have just landed some loopholes for the attackers to exploit. So these are the four primary fundamentals or reasons which I feel, which that the reason why we need or reversing, I can say professionals, or enthusiasts to look for the vulnerabilities in the existing system, right? Okay, so what is the reverse engineering process, right? Now, I mentioned that why do we need reversing, but let's focus on why do we, what is a reverse engineering process? Again, as I mentioned, that this is something which I learned from my experience. If you can also have maybe 2 different points or 5 different points on this, but this is what I believe works across all the reversing binaries, irrespective of whatever you do, right? So the first is locate the sources of truth, right? So when you are being given a binary, basically analyzing the functions, you determine that what are the possible sources of information you can get from the code itself, right? It can be any string, which can be helpful for you, or any print statement, or any statement, or any print statement, which the system outputs to the end user, right? Maybe you just parse those and see if it can help you in analyzing the actual in analyzing the behavior of the actual system. The second is determining the connections between what you know and what you don't know, right? Because that's what becomes now more interesting, that okay, you got some hints from the code itself with the help of some strings, but now how do you connect it to the things which you don't know, right? That is the most important thing, because it's just like a puzzle, that where you keep on connecting small dots, and at the end you get something, and then you feel, oh, this is what the system was supposed to do, right? And last but not the least, very important is to understand the unknowns. And when I mean understanding the unknowns is like a function which does not print any strings which are helpful. How do you determine the logic, right? It's not by just looking at the code, but also by debugging it, understanding what's the relation, what are the values which are being passed, other stuff. That's where the tools help, right? Because it just gives you a pseudocode, which we would see in some time, which just gives you a pseudocode, and then you identify the relationship between the unknowns and the knowns which you have. So what are the different binary forms, right? One is the ELF for Linux, other is the ARM processor, which is widely used in IoT space. The third is Windows EXE, which we are all very much aware of. And last but not the least, the APK files, right? So these are primarily, I won't say these are the only four broader classifications which we have. If you see, there is another a file called PCAP file, right? The network, which the network analytics folks use. That can also be one of the binary forms. Not exactly the binary forms, but at least those file is what would reveal some data. Yes, the kind of approach you would have for a PCAP file would be different to what you would have for ELF, ARM, or Windows, because it's like straightforward, right? You have like, I'm not sure if you have ever looked for a PCAP file. Maybe if time permits, I can show you. But it's like just gives you that what are the endpoints between which the communication is happening, and from there you can reveal some data, and determine that how the system is behaving. Now, one of the important factors where the PCAP can be helpful, right? For example, the home router which I was talking about. In order to determine that how the home router does an update from the internet, I just did a PCAP analysis, and I just came to know that which is the URL it looks for upload over the internet. And what I came to know was it was plain text. It was not an HTTPS. So those kind of things you can get from a PCAP file. But primarily, when you do the reversing, this would be the four primary object files, or the files which you would have in order for you to test your reversing skills. So today we would be focusing on ELF binaries. What is the structure? How to debug it in a with the help of different tools. That is what we would be focusing on. But as I mentioned, that going forward, I plan to cover each of these binaries in depth, and have some small challenges where we can test those skills which we have learned. Okay, so this is the ELF structure, the way it looks. So if you see here, it has a section header which tells which sections are in place. Then it has a program header, and then it has a executable header, right? So an ELF binary has a signature of 7F, which starts from 7F. From there, you would come to know whether it's ELF binary or not, right? So all these program headers, executable headers would make sure that those magic bytes are in place for you to determine that whether it's a ELF binary or something else, right? It's similar to all the files, right? Because if it's a zip file, we all have magic bytes at the start, which tells us that what kind of file this is. Similarly here also, the program headers tells you what is the ELF. I mean, it just tells you that the starting magic byte of this binary is 7F, which tells it's a ELF binary. Now, the most important aspect in ELF binary would be the sections and section headers. Not even section headers, right? Because section headers will just tell you which sections are in place. But all the code resides in the sections, right? Now, that does not mean that all the code which resides in sections, you can just, dump it and just understand what it is behaving, right? Because all this code would be in the form of assembly, right? And a longer code would have like 2,000, 3,000 lines of assembly language, right? And so you need to break. So it's not something that if you have just identified the section, which you can easily find out, you still need to understand what the program is doing. This structure basically helps you where to look for, as simple as that, right? Now, I won't spend much time here because that's how an executable header looks for. This is the structure. You can always, find this in the documentation. So as you can see that you can always identify what the executable header looks like by running this command read elf, right? So as you can see that it tells you what is the type of the object file. As I mentioned, this is the magic number where you have that 7f starting, which tells it's a elf binary, right? And then there are other parameters like, this, what is the type of machine, what's the object file version, and other stuff. Again, this is all this fields are not that important for us to understand. You just need to understand, okay, there's a elf binary. It just, and at the back of your mind, you just need to have the process in hand that, okay, and now I just need to look for the code which would help me in determining the relationship between the unknowns and knowns, right? This is how a section header looks. As I mentioned, that the section header would tell you what are the sections in place for the binary, right? In the next slide, we would see that which sections are important, but just remember that section header, you can always determine through this command. It tells you which sections are in place, okay? And as you can see here, that it tells you the section name, what is the section type, what is the flags and other stuff, right? This just a reporting, right? It just tells you that, okay, this binary has um, this sections in place and other stuff. I generally, when you start doing more reversing, you rarely use this commands. Basically, you just dump the binary in one of the tool which generates a pseudocode, and just from your experience, as you do more, you would understand, okay, you find few functions which are very important for you, and then with the help of debugging and a piece of paper, you just try to connect the dots, right? Okay, so as I mentioned in the sections, the three important sections is dot text. Dot text is where your main function would generally reside, right? Now, this is how the main function looks, right? Like, so what you see on the left, right? Left of main is nothing but the memory address at which this function is being loaded, right? Now, when you see something in this brackets, right, and this angular brackets, or and lesser than symbol, basically whatever you see between this, right, sorry, whatever you see between this, where you see the main is being written, it is nothing but the symbols of the function. What do you mean by symbols? Is basically an identifier of which function resides, sorry, an identifier of the function name. So the function identifier is nothing but its function name. What is the function name, right? Now, if you have, when you got a binary, and if you have a function name like this, it means it's a non-stripped binary. I would repeat, it means it's a non-stripped binary. What do you mean by non-stripped binary? It means the symbols are not being stripped. And what do you mean by symbols not being stripped is that you would have function sorry, function identifiers in the form of function names here, right? And say, for example, if you have a strip binary, right, it means you just have this memory functions, memory addresses, not the function names. And why it would be difficult now, just realize, right? Now let's consider I've given you a strip binary, right? And now in this case, just for a second, assume that you don't have a main being written next to the memory address. Now, though I mentioned that dot text would generally have the main function, it can also have other functions in as part of dot text, right? So let's assume that in dot text you have 4 different functions, which is strip binary. You just have memory address and the pseudocode, or basically the logic of that function besides after the memory address, like you see here, push RBP. Similarly, there would be 10-15 lines of that functions at different memory address. Now, the challenge for you is to identify out of those 4 functions, which is the main function. Because why? Because the symbols are now being stripped. You don't know out of those 4 functions, which is the main function, right? So that's where the strip binary becomes a more challenge. And we would see that how to locate the main function, even if you don't have symbols. And 99% most of the times you would get strip binaries, right? Why? Because if I've given you a non-strip binary, it means 50% I've made your job easier, right? Because like for example, say if I have built a crypto function which which encrypts your user input, right? Now generally, what do you think? What would be the function name of that encryption function which I would be doing? Generally, I would have encrypt or whatever, right? But I would have some resemblance to encrypt as a name. Now, say for example, I have given you a non-strip binary. It would be easier for you to just locate where the encrypt is happening, identify what exactly is happening in the logic, and that's it. You understand the logic, and then you can expose a system, right? So that's a reason that every developer gives you a non-strip binary, because it makes your effort a bit difficult, or makes your process a bit difficult to understand which function lies where, right? The other section is dot data section, where you would be initializing just the variables. Sorry, where you would just be declaring the variables, not initializing. So in this case, I've just declared the variable. I'm not yet assigned any value to it, right? Because the value would be assigned at the runtime. So that's the reason. So all those variables which gets a value at the runtime, I will be declaring in dot data section. And last but not the least is RO data section, which is a read-only data, where you would have the declaration of the variable and also the initialization at the same time. One of the example could be an array, right? As you can see that in this case, I have declared and initialized array in RO data section. Now, as it is a read-only data, you cannot modify it, right? But again, if there are any arrays which are being initialized, you can always look at this section. And even if you don't look at the section, you can always look for the references of this array in the different functions which is using it, and from there you can determine that, okay, what's the value for this array, which might be helpful in letting you know that what the exact values which function takes or uses it for to derive any output. And this would be one of the, as you remember the process of the reversing which we discussed, this would be one of the locations of truth where you got it from the function itself, right? Where you have some knowns, where you know that, okay, this array is being declared and this is the value which is getting initialized to, right? So this is how you would just help whatever data you can get from the binary itself, you just identify it and just note it down, so that it can help you later in determining what exactly this data is doing with the data which you don't know, or what we say as unknowns, right? Okay, now coming back to assembly basics, right? As I mentioned that you don't, even if you're not good at assembly, when I say you're not good at it, I don't mean that you don't know assembly, but what I mean is you don't know all the instructions which we learned, right? Or all the x86 instructions which we know, because it's practically impossible. Yeah, when you work more, you know that what each instruction does, but it could be possible that sometimes you might forget, right? So what I've done is this just a cheat sheet. Things which you need to know, bare minimum, right? That, as you know, that we can have a binary instruction which contains now the most important thing for Rx, right? You need to know that it always holds a return value from a function, always, right? This was very important, because when you call a function and when you exit out of the function, how do you know that what's the value the function is returning when you are debugging by looking at just the assembly code, right? So Rx always returns the value from a function. The other important thing is all these registers, like, right? RDI, RSI, RDX, in those order, like RDI, RSI, RDX, RCX, R8, R9. these are the registers which would be used to pass arguments to the function, right? As I mentioned, that first 6 arguments. Now, if there are more arguments, you would use more registers like R10, R11. But it's always important to know that whatever arguments you get from the functions would be saved in RDI, RSI, RDX. I mean, in this order, right? So this is important because imagine that you're debugging an assembly code and you get a value in RDI, right? And I mean, there is a function call which is happening, and before that, you see that some value is getting stored in RDI. You need to know that why it got stored in RDI, right? And you need to know that how it is going to be used. So if you don't know this, then it becomes a bit difficult. So that's very important to know, right? The other instructions, generally byte. So when you would have move byte, it refers to a 1 byte integer. Word is like a 2 byte integer, right? Double word would be a 4 byte. Chord word would be a 8 byte integer, right? So this is, I mean, this is important when you do. So we all know what a move instruction does, right? It basically moves a value from source register to a destination register, like move A comma B. It basically would move the values from B to A. But say generally in the instructions you would have move byte, move word, move double word, right? So you need to know that what exactly is doing. Either it's moving a 1 byte, 4 byte, or a 8 byte value. So this is another important stuff. Okay, now before we start, any questions? I know it's more of a theory, but just maybe another 15-20 minutes and we start with the hands-on, right? I would show that how do you analyze a binary and other stuff, but yeah, just bear for another 20-25 minutes, right? So I know early morning having this theory, it becomes a bit boring. So I hope it's been informative, and if you have any questions, I would just pause for a minute. Okay, perfect. So one of the important, as I mentioned, right, in a binary, you'd always have a functions, sets of functions, different functions, because it's a function where the logic of the program lies, right? Because we all learned that it's a function under which the prologue lies, the logic lies, the heart of the system operational behavior lies, right? So what what we look is what is a function, what are the parameters and local variables, how do you call a function, and what exactly happens in the memory footprint when a function is being called, what is a stack and stack frames, and last but not the least, what happens when the function returns. I mean, when the function is done executing, what happens when the returning from a function, what exactly happens from a memory footprint, right? So this is what we'd look for. Now let's see that, let's take an example of a sample function, right? Now in this particular case, I have an add function which is adding 2 integers, right? X and Y. And you can see that I have declared a variable sum, which would evaluate the sum of 2 integers X and Y, and then I am returning that value, right? So what are the parameters in this case? X and Y. What are the local variables? It's sum. Why local? Because it's being declared within the function. And this is the return value of that addition which is happening, right? Okay, now let's see what happens when you call a function, right? You push parameters on the stack. You jump to the entry point of the function. You execute the function code and then return to the next statement after the function call, right? This exactly what happens, right? So first you push the parameters, you jump to the entry point of that calling function, you execute the code, and then return to the next instruction after the function call, right? Now this exactly what happens. So as you can see that this was the function which is adding the 2 values 3 and 4. And so when you call this function, it goes to the prologue, executes the function code, and then returns it to the next instruction after the function call, right? Now let's see that what exactly happens in the memory footprint, right? So this is a stack pointer, right? I hope every one of us know, right? What is a stack? It's basically a memory container, you can say, where you load maybe the program variables, or basically the heart of the program lies there, right? Because each program has some kind of stack memory from the x86 architecture, where you'd be storing the values, storing the outputs, storing your logic, right? And how it is being determined, it's basically there's a stack pointer which tells you that, okay, what is at which location currently the stack is pointing to, and at which location your values would be stored at, right? So that is your stack pointer. So generally, yes, the stack pointer would point to the top of the stack as usual, right? And there is a base pointer which points to a region within the stack, right? So generally, stack would be pointing to the top of the stack, base pointer would be pointing to the base of the stack, right? Now, what is the first thing which happens, right? When I call the add function, the parameters 3 and 4 are being pushed to the stack, right? Which means now the stack is being decremented to so an integer holds 4 bytes of memory, right? So it would just decrement by 8 bytes. And now it would point to the top of the stack, where once the values are being pushed, right? Which is 3 and 4. Now I call a add function, right? Now what happens is, before I call the add functions, what it does, it basically saves the instruction pointer into the stack. Why this is important? Because as we saw that once the add function is being executed, it should know that to which instruction it should execute after returning from the add function, right? So that's where the previous instruction pointer is being saved. It's something that, for example, um, like say for example, you're going to meet to a friend, right? So say for example, you need to meet two different friend of yours, right? And say you meet one friend from say 10 to 11, the other friend you meet 11 to 12. Now what after that? You need to know what you need to do after 12 o'clock, right? Unless and until you don't care and you just keep on wandering, and you just keep on just roaming around. But ideally you would like to know what's your schedule, right? That's what EIP does. That once you meet those two of your friends, what's next? What is your return point? Like after 12, what do? You come back to your home, or you meet another friend, right? That's what your saved EIP does. That I before I call a function, what is the next instruction which I need to execute before I before I return from that function, right? So that's what the EIP does here, right? It tells you that which is the next instruction you need to execute once the add function is done. So this is how the prologue looks, right? So as you can see that it stores the old EPP which was there, because if you see here, currently this is the EPP. Now in this case, the old EPP is now being saved here, because you need each new function would have its own stack pointer. I mean, the stack pointer and also the EBP, the base frame for that particular function. So that also gets saved here. And this is how the prologue looks. You see here, old EPP, this was the instruction pointer. And then these are the parameters which are being pushed for the add function. And now the local variable gets pushed, which is sum, where you would be storing the values of your addition, and then the rest of that remains same. Now if you see here, this is how this is what we called a stack frame. What is a stack frame? This is nothing but a which would have its own ESP, its own EBP, and different variables which are being pushed to the stack as part of that function. So each function would have its own stack frame. So if I see here, starting from this ESP to this, it's the frame of add function. Similarly, from here to here, it's a frame of main function. If there is a third function, it would have its own stack frame, which would start from stack pointer and would end with whatever variables I have initialized or declared. Right? Now, coming back to the binary analysis, okay, we looked at the theory, what the assembly looks like, what a function call does in the memory footprint. Now let's understand that what's a difference between a static and dynamic, right? Now, what do you mean by static is that you got a binary, you just load it in some tool, or you just maybe analyze manually and then try to identify the connections between them, right? Or try to connect the dots, what exactly the system is doing. Now, generally, you would have deassemblers for that. Now, what do you mean by deassemblers is, generally people have this question that what's the difference between deassemblers and debuggers, right? So deassemblers is nothing but which would basically take your binary, generate a pseudocode for you. What do you mean by pseudocode? Is like almost similar to the source code what the developer would have built, right? Now, and the language which it uses is generally C. So all these tools which I mentioned here, right? Be it Ghidra, IDA, Hopper, Radar tool does the same thing. It basically takes your binary. It can take any binary, right? Like for ARM, currently Ghidra has a new release which supports it. But generally, all the others, you need different plugins for different reversing types, right? For ARM, you need different um, plugin for it, right? And for exe for Windows, these tools are better, but for Windows there is another tool, debugger, which is better than this. I've just not mentioned here because for now we are not covering the Windows exe, but whenever we cover it, I would take you through that tool also. So I hope that's clear that what deassembler does, right? It just takes your binary, generates a pseudo code for you, which would be almost identical to the source code with the developer has built. And why this is important is because with the help of this, now you don't have to take the pain of going to the assembly language, right? You can just look at the pseudocode and try to find the relationships if there are any, because yes, one of the primary requirement would be we know some kind of C coding. And even if we don't know, with experience, we come to know, right? That what exactly this is doing, or we try to search that what exactly this piece of code is doing, right? So this deassemblers makes your job a bit easier, not simple, but at least it gives you some hints to start with and what to look for. And what do you mean by dynamic analysis is where just static analysis is not going to do, right? You need to run the function to understand that what values are getting stored in the registers, which we saw a few slides back, right? Like what is getting saved in Rx, if a function is being returned, what are the arguments which are being passed to the functions, and what values it is, and basically what it is doing with those arguments. And that's where our the most trusted debugger GDB helps, right? The reason I mentioned here advanced GDP is because this is a plugin of GDP Jeff, which you would see in some time, in few minutes, that why it is helpful, right? Because I'm not sure if any of you have used a traditional GDP, which we had. It has all the features, but the only problem with that was you had to print the register values every time, like info registers, to look at what the values are being passed in that register, right? But with this plugin, the moment you go to the next instruction, it just prints all the values of the registers where the values got changed, right? And that also in a %s format. It also gives you a string format next to it so that you can correlate what are the values which are getting passed in those registers. So this is where this plugins would help. So generally, most of them now use this plugins and no one use the traditional GDP which we had. So generally in a binary analysis, right, you'd always do a combination of both. It's very rare that you'd get everything in static analysis, right? It's very rare. I would share, we would see in few challenges where static analysis gives you everything, but mostly you would also need a debugger in most complex binaries to understand what values are being passed in different registers. And you'd do both hand in hand. right? It's not something you do static, say separately, dynamic separately. That's not how it works, right? And the other important thing is now you have just 5 tools, right? Which tool to go for? I mean, yes, today as part of the session, we will be covering one tool, but what tool you would go for? Generally, you'd always, I mean, I always go take 2 tools at the same time. First, I load the binary, say in Gidra, and see if I'm getting some useful information. If not, then I would maybe dump the binary in IDA, because sometimes the DSMLers are also not able to reveal what it's supposed to. I mean, it cannot understand the source code, and that's the reason why it cannot generate the pseudo code for you. So generally, you would use a combination of DSMLers, and also at the same time would do dynamic analysis almost at the same time once you have understood what the function is doing, right? Okay, so too much theory. So I mean, what's the time? 10 o'clock. Okay, perfect. So let's take the hands-on, right? Which is some excitement should be there, hopefully. Okay. So as I mentioned that today I will be covering the tool which is called Gidra, right? Gidra is something which has been built by NASA, sorry, not NASA, NASA, and it's free of cost, right? And I would just so this is what the console of Gidra looks. It's been built on Java. We would just look through what each piece does here, right? So maybe the Gidra installation is straightforward. There is a documentation of Gidra that how do you need to install. The only requirement is you need to have a Java 11.0, right? And if you're using a Mac, it makes your PC damn slow, right? So make sure you're putting it on a Linux, because the performance is better as compared to Mac, right? Yeah. So this is how the Gidra console looks like. Now you can always create a new project here. That is something which is generally which happens in almost all, right? So in this particular case, my project name is I've called reversing. So if you want to, yeah. So this is a project which I've created, offensive, but you can always create a new project here, and then can do a next, and always create a new project similar to what we do in any development environment, right? So I won't spend time in that, but that's how you create the projects, and then you load the binaries which you want, right? So you just do import file, and you load the binaries which you want, correct? Now this dragon icon which you see, right, this is nothing but a code browser. It is nothing but a plugin which would parse the binary and generate the pseudocode for you, right? So whenever you load the binary, you just need to drag drop here, and it would just throw a pop-up of whether you need to analyze this binary. You just need to press yes, and once you press yes, after a few minutes you get this what we are seeing here, correct? Okay, so let me quit out of this. I hope you can see my screen. Okay. So this is my Ubuntu virtual machine. The reason I opened Ubuntu machine is I wanted to show you the GDB also, right? Debugger. Okay. Now I have 5 challenges here. Reversing 1, 2. Yeah, I won't show you the source code. So these are the binaries, right? So we would just go each binary one by one and see what we learn from each of them, right? So let's learn the first one, right? Reversing 1. So if you see here, the first thing what you do is determine what's the file type, right? Which we generally do. So as you can see that it tells you that it's a ELF binary. LSB means it's starting from left architecture, left bit architecture. And as you can see here, that is being used x86 architecture. And the most important thing is stripped, right? Now, as we know that what was stripped is basically we won't get the symbols or the functions what it is doing, right? Now, you can also check, there's a obj dump utility, right? Where you can deassemble all the what is basically all the functions, or basically all the symbols which are there. You can just look at it by running this command obj dump, which would tell you that what's the file format, and it would now show you all the deassembly of the sections, right? If you remember, sections where the one like .text, .data are the sections where your code resides, right? So this is how it would look like, right? And as you can see that everything is an assembly, and each section you would look, you would get to know for. Like for example, this is, let me show you, yeah. This PLT section is there. This init section is basically the function is getting initialized, your program is getting initialized, right? Then see, as you can see, there's .text, right? Now generally .text is what I mentioned is would be your main function, but your .text can also have a combination of other functions, right? So you need to determine that where exactly the main function starts from. If you don't have the symbols, right? In this particular case, we don't have the symbols. If there was a symbol, you would have known a main function next to the function call, but that's not the case. So, and this is the RO data section where you have read-only data, where some values are being initialized, right? So all this information, I mean, you can use obj dump tool, but all this information you would also get from the deassembler, right? So it's just a choice which one you need to go for. If you're more comfortable with the assembly, go for obj dump. If you need a combination of both assembly and the source code, then deassembler is the right tool for you, right? And this is a data section. Okay, so we came to know that this file is ELF binary, right? Now the next what you look for is strings, as I mentioned, like locate the sources of truth or locate the information which you can get with the help of the binary itself, right? So what I do is reversing one, and I would see if there are any strings which are helpful to me, right? So if you can see here, it just tells me what's a libc uh, object file which I'm using, and then I see something enter the password, right? And then I see a string called I cracked it, right? And then it says access granted. So the and yeah, rest it just tells me what are the different sections, right? Like .data, .ro data, and other stuff. But this looks interesting, right? And believe me, you won't get all the, you might get sometimes hints in the strings itself, right? That what exactly the function or known strings which are being used by the binary itself. Now in this case, what I understand is that this binary is accepting some kind of password, right? And maybe I cracked it would be the password for it, right? So let's see if it works. Copy paste doesn't work. I crack. Perfect, right? So this was as simple as it can be, right? Because what you did was, but again, you need to determine, you need to know that, okay, strings can give you the list of strings. So what strings does is basically it just lists out all the strings which are being used as part of this binary. And one string which I identified was enter the password. The other is potentially it was the password and which we used and we got the access, right? So this was as simple as it can be, right? You didn't wanted a deassembler. You just looked at the strings. You just guessed that the password is I cracked it, and yeah, you solved the first challenge. But that's not how simple it would be, right? Going forward. So let's look at the second challenge, which again asks for some password. And it says access denied, right? So we again follow the same path. We do file reversing to, we see that again it's a elf binary and it is being stripped, right? Now if I do a strings on reversing 2, so as you can see, again it asks for a password, but this time I don't have any hint in the form of what password it can be, right? It just says access granted or denied and nothing else, right? Now here, now you need to actually look at what this binary is doing, right? Okay, so what we do is we just load this binary in Gidra, correct? So as you can see that I've loaded here a reversing 2 in Gidra. As I mentioned that how when you launch the Gidra for the first time, you have to create a project and then you have to import the file and then run this file across this dragon, which would then give you this. Okay. Now, what does this show, right? This is the Gidra console. And as you can see that this is a symbol table on the left side. Basically, it tells you what are the different functions which are being in use, right? Let me have my charger. Yeah, so it just tells you which are the functions here, right, on the left, which are the functions which are being used. Now, as we know that it's a stripped binary, we are not going to get symbols straight away, right? We are not going to get the mains function. As you can see that this is how you would go look for, and this is how the names would look like. Now, here you need to identify which is a main function and which is the main, which is the other function, which basically parses your password or checks what should be the actual value of the password, right? So this is how the symbol table looks. This is your data type. What are the different data types which are being used for different variables, whether it's a char variable, int variable, and other stuff. You can also define your own data types. Like you can also define your own structure or own data types in this data type manager, right? Now, this is the first thing which you would look for. The other thing is Gitra also has this defined strings option, which is similar to what we did in strings, right? Strings and yeah. So as you can see, mine is lagging a bit. Okay. So as you can see that what I did was I did a defined strings, which was similar to strings in Gitra. Sorry, in here what we did, right, in Linux VM. This also does the same thing. It basically tells you the list of different strings which are in place for uh, in the code. As you can see that you can see enter the password, access granted, denied, and you can always click on this and see that where it is being defined, right? So you can always do this. So this is one other option which you have. The other is what do you see here in the central pane is basically the whatever it has
Me, sir.
parsed, right? Now, as you can see that as I mentioned that the magic bytes of ELF binary would start from 7F. So as you can see that it starts from 7F and tells you that it's ELF. And these are the different structure variables which we saw, right? The structure, like what is the entry information, what is the magic bytes and other stuff, right? So this is what you would see in the central plane, which would be in assembly. But on the right side, you would see the pseudocode. Currently we don't see anything, but you just now quickly understand how to get the pseudocode. So I hope this is clear till now. When you launch the Gidra, the first thing you would see on the left is a symbol table, data type managers. On the center there would be a machine assembly or the assembly code of your source file, and then on the right it would be the actual pseudocode which would be in C, right? So currently you don't see anything, but quickly you'd realize that how the source code looks like, right? Now, be it generally in a strip binary, right, you'd always have an entry function, right? Entry function is like from where the main function would be called, right? So you click on entry and you see the pseudocode which is generated on the right. As you can see that it's a libc main, which is calling a main function. And there are different arguments here, right? Many arguments. Now, generally, the main function would be the first argument in a libc start main, right? And the way you see the address for that is this 217, right? So as you can see, generally, so what we learned was before the function is being called, the arguments are being passed in different registers, right? Like it does not matter where it gets saved in RDI, RSI, but this is the, this is a flow, right? That before calling a function, I have to store the parameters in a registers. Similarly, as you can see that in this case, I'm calling a libc start main, which is here, right? This one. And before that, whatever you see this LEA, right, which is nothing but load effective address, what it's doing is it's basically storing the arguments which would be used in calling the libc start main. And there are 3 arguments, right? Because I see 3 addresses being loaded in 3 different registers, which is R8, RCX, and RDI. Now, generally, the main function would be the last argument before the function is being called. So if this is the where the libc start main gets called, this would be the function of your main. This would be the memory address of your main function, right? But again, what this deassemblers do is it just loads the memory, it loads a binary and just generates the address randomly. For Ghidra, it starts the memory address numbering from 0010, right? But that's not how it would when you would actually launch the binary in a VM, right? In a Linux VM, the memory address might change, right? So how do you identify that what are the actual address? That's where, I won't say challenge, but you need to make sure that the memory address which you're looking in your debugger should correlate to what you see in the deassembler. Now, as I mentioned in deassembler, they use their own values. Like, for example, IDA uses a different start memory address, Ghidra uses a different start memory address. But your actual VM, or where where you load the binary, right? It would generate the memory address on the fly, right? Because it's not going to use the same memory address what your deassembler is going to use, right? So you need to find the relation that where the main address is actually pointing to. Yes, you got some hint from the deassembler that, okay, where the libc start main is being called, the instruction before that is where the address of the main would be loaded, right? So let's dive into the world of debugger, right? So what I do is I do GDB reversing perfect. So as you can see that I have already installed this Jeff plugin. That's why I got this Jeff. Otherwise, you need to install it. So it's pretty straightforward. There's a documentation for it, right? Now, if you see here, no debugging sessions active means that the binary is not yet loaded. We have not started the binary. We have just done GDP reversing 2. So what I do is, in generally GDP, you would run it, right? And if you have ever used GDP, you would always run the program within the GDP framework. But in Jeff, there is a command called entry break, which means that it would look for entry instruction and it would break it there. Okay. So let's run that. Now, as you can see that now it was running the binary. I just stopped exactly at the point where it found the entry instruction. Correct? When I say entry instruction, basically it found the entry point of the program, right? Now, as you can see that the memory address here and the memory address here is completely different, right? Yes, the suffix is same, but the prefix is completely different. Why? Because on an actual VM, it's on the operating system to tell you that which memory address this would be loaded, right? That's completely dynamic, right? Now, how do you identify the relationship which becomes very important, right, for you to debug? Now, the first thing which you would see is VMAP. VMAP is nothing but is basically tells you that what is the start and the end of the memory address at which the function is being loaded, right? So as you can see that the start and end of my memory address loaded is reversing 2, right? So the start address was this and the end address is 6000, right? So basically this is what we see here, right? And the another thing is you get to know that what's the stack address and other stuff, but this is very important, right? You know that what's the start of your memory address would always be this, the 5000, sorry, this one, the first line, starting from 4000 to 5000, and then from 5000 to 6000, it just gives you a range, but the starting point is this 4000, right? Okay, but the entry point, it's not starting at 4000, it starts somewhere at 50A0, right? And if you see here, this instruction is similar to what I see in the DSMler, right? 0A0, correct? Now what I do is I need to know that what's the address of the main function, right? So what I do is I just do a next instruction. So ni is basically tells you to go to the next instruction, right? So I just go here, I just take couple of steps. Okay, now this is what you got, right? So in DSMler, we saw that there were 3 arguments which were getting saved, as you see here, right? LEA, and then I'm calling the libc start main. And what did I mention? That generally the address of the memory function would be one instruction before when the libc start main is being called. So which is this, right? So in this particular case, that memory address is, as you can see, in 0C1, the address in this register is being loaded to RDI, and that address is this. So this is nothing but your main function. So what you do is you copy, you break at this point. So generally the way you do a break is you do a break star and the address where you want to break at, where you want to halt the programming execution, right? The program execution. Okay. So I've created a breakpoint here and now I do a continue. Now, as you see here, now it has exactly stopped at the 217 location, which is my main function, right? So if I go here and if I click here, this is nothing but my main function starting at 217 and whatever you see here, right? Enter the password and other stuff. This is what nothing but my main function. Now, as you can see that it is not generating any pseudocode on the right side. Why? Because it doesn't see any useful information for it to generate the pseudocode, because as you can see that it's a bunch of moves, subtract, and XOR instructions, and maybe it could have given the pseudocode where scanf, it does a scanf and says enter password, but for some reason it doesn't generate the pseudocode, which generally would be the case, right? You would not always have a pseudocode generator, and that's why I told that you generally use a combination of DSMlers. Like you try to load the same in IDA to see if it is generating the pseudocode or not, right? But let's see. I mean, it has not generated the pseudocode, so does it mean that's the end game for us? No, right? Let's see what other hints we have. Okay, we know that it's asking for enter the password, argument from user. It calls puts called fgets, and then it calls this function, right? 1189. Okay, so I would show you again. So always, if you want to go to the back, one instruction back, you can always click this arrow, this one back, right? On the, I mean, one step back. So as you can see that the reason I went to that function is because I was not getting any pseudocode. I saw that, okay, it's accepting any argument called enter the password. So I call this function 1189, right? And now I see some pseudocode here being generated, right? Similarly, if you compare here, that function is nothing but this one, right? 6004. Now, if we need to compare, yeah, so it's at 264, right? And we are at 239. So if we go a couple of instructions back, yeah, this is in general puts, so we are not interested in that. Yeah, generally you won't do next instruction. You just create a breakpoint at the memory address you want to go for. But I'm just, since we are doing it for the first time, I just wanted to show that what at the start what you do, right? So this is the function, which is basically which gives some information for our password. As you can see, the suffix is 264, where this function is being called, right? So what I do here is I just do a break. And I do a continue, right? Now, as you can see, right, this is the function which we wanted, right? 189, 189. So I would just click here. Now, as you can see, what I mentioned that any arguments on the functions is being saved in registers. So these are nothing but the arguments: RDI, RSI, RDX, and RCX, right? So yes, these arguments, what currently it just does not make any sense what these values are, right? But as you can see that the debugger just tells you that this were the arguments which are being passed to this function. And as we just uh, saw in few slides back, it's being saved in this registers, right? So in order to go within the function, you just go SI. So you just go inside the function and try to identify what's the logic it's doing, right? Now, this is what it's doing. As you can see that 189, it's 189. So we are inside this function, which would help give some hint for our password, right? Now, we also know a pseudo code, which is now being generated. Now, as you can see here, there are some revealing strings or ASCII characters here, right? So which starts from I. So as you can see that what it does is it's there is a value which is being loaded in AL, which would be your input. It would be compared against this ASCII character 69, which is I. Similarly, the next uh, value would be compared against G, right? So whom we are comparing this with, right? Now, what does AL would hold? AL would hold, or this register would hold our input. Now, how did the input came to this function, right? It would have passed as an argument, and that's the argument which is being saved in param1 variable, right? So if you just look back, as you can see here that before this function was being called, I moved some variable value in RDI, right? And this RDI, and what was the value in RX? What it can be? It can be our input, right? Because the program is expecting you to enter something. So you enter something, that value gets saved in RX, which is now being saved in RDI, and that is being passed to this function, which is being saved in this param1 variable. And this param1 variable, which is an array, is now each character is being compared with different ASCII characters, which is your actual password, right? Um, that's what it is doing, right? First it is comparing with I, then it is comparing with G, then it is comparing with O, right? And if everything matches, then it returns a value, right? We all know that if it returns 1, it is true. If it returns 0, it is false. So in this particular case, my input should be what? it should be a addition of all these strings, right? Oh, sorry, all these characters, which is I, G, O, T, T, H, I, S, right? So basically the password is, I hope you're getting right. Now, the same thing you can check here also, right? That we have a compare this AL69, right? Now, do you now realize the importance of DSMler, right? I mean, you realize the importance of this pseudocode which is being generated, because it was very easy for me to just look at it, right? Okay, it should, the input should be should have I, G, O, T, 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 H, I, S, right? But let's assume that the pseudocode was not there. Like, let's assume that, let's assume that you don't know this right side. You just had this assembly language. Then what you had to do was, you just have a piece of paper, do a static analysis, and then just determine, okay, the first value which is loaded is 69, the second value is loaded which is 47, and then you build, you see what values are being passed, and then you have a hint in this sense, right? That jump not zero, it means if it is not equal, it would come out of the function. And if it is equal, it would execute the next instruction. I would repeat what I mentioned here is, let's assume that you don't have the pseudocode, right? And you just have this debugger. And now you somehow identified that this is a function which would give you the real password, right? And the another hint is that you have some ASCII character being compared with your input, right? Which is being saved in AL. So what you see here is that the first thing, it compares with 69, and then there is a jump not zero. So generally when a comparison happens, you would always have two conditions, right? Whether it matches or whether it doesn't match. So in assembly, that's how you notify it to jump not zero or jump zero flag, right? Jump zero means it's equal, jump not zero means it's not equal, right? So if these two values are not equal, you just, as you can see, that it just jumps here, which is out of the function. But if it is equal, it goes to the next instruction, right? That's how, I mean, as I mentioned, that if you don't want to look at the pseudocode, this becomes a bit difficult. I'm not saying that it's impossible, but difficult at the start. So that's how the pseudocode helps you to tell that, okay, because now you don't have to look at the bunch of assembly functions. You just look at this if statement and you come to know that, okay, my password is this, I got this, right? So that's what we do here. I got this. T was capital T. Cool. So as you can see that this time we did not got any hint from strings. So we had to actually debug the code and also understand the value or the importance of the DSMLers, right? That how the pseudocode which it generates is useful. So what did we learn from here is, how do you load, how do you analyze a binary in a DSMler? This is nothing but a DSMler which basically parses the logic of your function and gives you the pseudocode in the form of C, correct? And what did we learn? Another thing was, how do we load it in GDP? How do we, the most important thing is, how do we identify the main function? What is the entry point? What's the memory location? Because as I mentioned that each DSMler uses a different function. Sorry, a different memory address to start with. So you need to correlate that with your debugging environment so that you run it side by side, right? Say for example, you want to debug this instruction, you go to that memory location, which is this, and then see that what exactly is doing, right? Now let's look at other binary. Let's look at, yeah, let's look at this. That's interesting. Okay, so this is reversing 3. I think the time is 10:32. I will take 5 to 7 minutes. Okay, so again, this binary also expects you to enter some password, right? And it says access denied. So we follow the same steps. We say that what's the file type, elf strip, right? So now we do strings. So as you can see that again, strings, we know that it's accepting, asking the user to input some password, but it doesn't give any hint, right? It just says access granted or denied, right? So similar to the last challenge, let's see what difference this time it brings us to, right? So as we know that each program starts with an entry point. So we go to this entry point. I just do a double click here. So this is the entry point, right? Now, as we saw last time that this is the address where the main starts. So let's go here. Again, no pseudocode generated, right? Because it feels that nothing is important, right? We know that it's asking for a password, but again, similar to last time, there is a function and there is an argument which is being passed. And we all know that this argument which gets passed to this function is the input from the user, right? Now let's look at this function. Okay, now this time the function logic is a bit different, right? So as you can see that it starts from here. Okay, and similarly, the thing on GDP remains the same. We do entry break. Okay, and it stops at the entry point, right? And we identify the main function from it. Okay, now as you can see that it has loaded some pseudocode for me, right? Now let's analyze it, right? So it starts from RBP. Generally, the start of every function, you would have some sub RSP being decremented, right? Now you move, there is some value which is moved to EAX. Now there's some interesting here, right? There's a load effective RDX and there's some this variable. So let's click on that, right? And what we come to know is it's nothing but a data segment. Data segment is nothing but a variable which is being declared and also initialized. And what is the value for that is some this random ASCII string, right? This string, okay, which is helpful for us. But we know that there is some string which is loaded in this variable which is saved in RDX, right? I mean the address of that location is saved in RDX, right? And you also come to know the value here itself rather than going there, right? That this is the value which is being loaded. Now, okay, now this is where this is getting loaded, right? Now, if I look at the pseudocode, let's see what it tells me. It tells me local 20. I go to the while loop. I first determine the length of my input. Param1 is nothing but the input, right? Which is being passed from the main to this function. Now, what I do the first time is I check whether the length is less than the variable local 20, right? If it's less than or equal to 0, I less than or equal to this variable, I return 1, right? I exit out of this function. Or if it is 0, if it is not less, what I do is in this variable, right, local 1c, which is another variable, what I do is this is what local 20 is nothing but the first index of this array, right? So if you see here, this is an array of integer type. And what I'm doing is I'm taking the first byte here, C, and then adding a 10 to it, right? A decimal value 10 to it, and I'm saving it in local 1c. Now I'm comparing whether that 0x7a is less than local 1c or not, right? There's just some hexadecimal value. And if it is less, what I'm doing is the first index, because local 20 is still 0, right? Is the first index of this, which is C. Now, what is the new value it holds is like C plus 10, I do a negation, I subtract it with hexadecimal 10, which is nothing but 16, right? Decimal 16. So I subtract with that and save the value here. And then local 1C, at the end, I basically compare it whether, basically I compare local 1C if it is so basically I compare, so okay. Initially what I did was in local 1C, I took the first variable, right? C. I added a decimal 10 to it. Then I subtracted and then I compared whether 7xa is less than or greater than. If it is less than to the value which I got, C plus 10, if 7a is less than that, then what I do is I subtract 16 to it, right? This is this if loop. And what do I then compare is whether this is equal to param 1, whether the value is equal to C. If it is equal, if it is not equal, basically I break out of this loop, right? And if it is, basically I break out of this if statement and then I add the value of local 20 to local 21, right? So in a sense, what we are doing is I get the value of this, right? So this is my integer array, right? So the first thing what I do is say, consider there is a variable 0 and say the flag is this. Why I'm not able to type? Okay. And say this value is, I would want you to, I won't reveal the answer this time. I would want you to, solve this. It's not that difficult. So in this particular case, what is happening is the first time, right? What A holds is A equals P of 0 plus 10. And then I compare this value with if 0x7a less than a. And if it is less than 7a, what I do is a equals a of minus 16. And then I compare this a with, if it is, yeah, maybe, if it is not equals P of 0. And then break. Cool. So this loop runs till the length of this array, right? So basically, if you see that, what I'm doing is I'm taking each element of this array, doing some computation, and then placing it back to my end variable a, which I would be returning it to main, right? And that would, after this computation, whatever value which gets resulted would be my password, right? So that's what we understand from the pseudocode. Is there any questions, right? I would just go through the pseudocode quickly one more time, right, before we wrap up. As you can see that while true, normal while function, right, in C. And as you can see that in the assembly, right, how do you determine, just looking at the assembly, whether it's while, for, or other stuff, right? It becomes a bit difficult because if you see here, okay, you are comparing something. So this is a while loop. So the while loop starts at this point, right? So you are comparing something. So in order to see that what is getting compared, you need to see in the debugger what value gets loaded in EX from AL, right? And then if it is jump 0, you go to this function, which is add. And if it is not, you move, the next instruction is you move EX to 0, right? But if you have a pseudocode, you can quickly see that it is true. And in order to learn that how the pseudocode relates to assembly, this is how you go for it, right? You just click on it here and then correlate to what is the assembly instruction, it is getting generated. So next time when you see a jump 0, you at least have something at the back of your mind that, okay, it might be a while loop, which it is comparing something, and it's returning some value. So in this case, it was while true. I'm storing the length of the input which I have, and then I'm comparing it with the local variable which I have initialized, right? And then this is where the actual thing starts, where I'm taking the integer array one index at a time, in a loop, doing some computation, mathematics to it, and then storing it back to the variable which I'm going to return to the main function, which would give me the password. So maybe I would share this binary, the other two binaries also, reversing 4 and 5. See if you can solve it. If not, maybe I can share the solution and the detailed steps how to go for it. But I would suggest that, so the action items on you as participants would be to get the password of this. That this is the jumbled string. You need to unjumble it. You need to find the correct string, which is your correct password, right? And the next two challenges is, one is a non-strip binary and one is a strip binary, right? So you get a hang of both. And yeah, I would suggest that, yeah, with constraint of time, I cannot go through these two challenges, but yeah, I would suggest if you want to learn, you can just try it out. I can just share those challenges and also the documentation how to install the Ghidra. And maybe what I can do is I would also share the Linux, the Linux OVA file itself. So you don't need to install these tools. It's already available. You just need to deploy the VM and just try out these challenges. And maybe a week later, I can share the solutions to my notes, sir, and he can share with you folks. So that's the end of the session. I hope it was informative and some learning for you folks.
So thank you, Bhavik, for, yeah. So there is some question we will quickly, I can read. We can take couple of them because Mritunjay has already joined.
Sure.
So is there any upper limit in the size of ELF file which can be disassembled in Ghidra, etc.? Something like that.
There's no upper limit. You can deassemble any big files. There's no upper limit on that. But the only challenge which you would feel is, as you saw here, right? For sometimes for some binaries, you would see that Ghidra is not able to generate the pseudocode, right? Now, if you're more comfortable in looking at the pseudocode, then you have to look for IDA, because generally IDA works for all the binaries. I mean, that's what I've seen. Like more complex binaries, when I say more complex binaries, the binaries which are obfuscated, right? Or the binaries where consider a binary which you have got for a customized x86 architecture, where he has just made modification to the operands, and which it it would be make more sense if I show you, but maybe sometime when we have more in-depth session. But just consider this, right, that you have a customized x86 architecture where what I have done is I have basically changed the behavior of the move instruction, where in place of move, when you do move a b in my architecture, now it does add a of b, right? So those kind of complex binaries, you generally go for IDA, because Ghidra does not give you good pseudocode. And for those complex binaries, you need some kind of pseudocode to start with, right? Because otherwise, as you saw that looking at the assembly, it's not that difficult, right? But it's just time consuming. You just need to build those flow diagrams with your pen and pencil, right? And then determine and then connect the dots. So that is the only challenge which you feel, and that's why mentioned at the start, right, that you would always have a combination of deassemblers. You would just not rely on Ghidra. You would have Ghidra and IDA open side by side. You just load the binaries on both and see from where you're trying to get the most sensible information out of it, and then you use that deassembler, and you have a debugger. You start analyzing it. So, but yeah, there's no upper limit on any of the deassemblers. At least I have not seen it getting crashed.
Thank you, Bhavik. Since Mritunjay is already there, so
Sure.
we can take the remaining questions so later. So indeed, it was really great to hear, and also we have heard you previously. Uh, so I thank you on behalf of the Department of Computer Applications, Cochin University of Science and Technology, as well as on behalf of all participants present over here. So it was a great learning lesson, and hope to hear to you in future also, Bhavi.
Sure,
Thank
sir.
you so much
Thanks
for
a lot.
joining. Thank you.
Yeah,
Thank you.
thanks a lot.
Thank
Have a
you.
good day.
Yeah. Bye-bye. Take care.
Bye.
Bye. So good morning all. We have our next speaker, Mr. Mritunjay. He is an entrepreneur with over 10 years of experience in network security. He currently works as a subject matter expert with Cisco customer experience team. He is passionate about learning and creating new things, customer transformation and engagement, leading transformation of technologies, customer solution, driving automation and innovation, and spearheading product serviceability to deliver high quality customer centric services solution product. His focus areas include cryptography, PKI, and enterprise security. He has been a speaker on cryptography for educational institutions such as SIT Timkur, and has conducted sessions on network security in Cisco SICON event. Mritunjay, I invite you for your session, and thanks for accepting our invitation and being prompt to share your valuable knowledge with us. Thank you, Mritunjay. Over to you. We can start.
Thanks, Vinod, sir. So I think my audio is clear. Am I audible?
Yes, we can hear.
So let me present my screen. So is there an option I can share my screen? No. Okay, here I got it.
Yeah.
I have to quickly rejoin the meeting.
No problem. No
just
problem.
to share
No
the
problem.
screen.
No problem.
Okay. Are you able to see my screen?
Yeah.
Okay. So, hi everyone. My name is Mritunjay Sethi. I work as a, subject matter expert with Cisco security domain. I have been with Cisco from past 6 years, where I joined Cisco in the year of 2015, and I have been working in the security domains since then. And I have an overall experience, as mentioned, of 10 plus years. And my daily job in Cisco involves interaction with different interdepartment views in order to how can we have a better customer experience, how to uh, make our products or a feature implemented in a better way for either troubleshooting or for customers for better understanding. So I come from the land of Odisha. It's the eastern part of India, and that place is famous for its temples and sweets, and we have some fabulous beaches as well. So if you ever get a chance to visit Odisha, do visit Odisha. With that, let's jump into today's session, where I'm going to take you on a journey with Alice and Bob in the land of crypto. So as you can see, the topic or the headline of my presentation is Alice and Bob in Cryptoland. So the official designation of mine in Cisco is technical consulting engineer with customer experience. And one best thing that Cisco has given me is they have given me a lot of respect when they generated my ID. So if you can see my Cisco ID, there is a lot of respect that they implemented. Like my ID is Mritunjay. So I go by the name in the organization. So most of the people, they don't call by my first name or by last name. It's a little complicated for you guys as well. So I go or I get recognized by my ID, Mritunjay. So what we are going to learn in today's session, or what is the session is focusing on. In today's session, okay, everything is over the internet, and internet is a highly unreliable and unprotected medium where anyone can sniff in, anyone can look into what information is being exchanged between entities. So cryptography is a mechanism, okay, which is implemented in order to provide you secure data communication between entities, and how to validate that your data has not been tampered while getting transferred from one location to the other location, or how securely can I save my data. It may be on a flash drive, it may be on a hard drive, it may be on a database server. So what does cryptography equips individuals, or how does cryptography helps you in order to protect your data? So with that, let's look at some of the mechanisms, okay, which the cryptography is equipped with, okay, in order to provide secure data communication or for securing your data. So what are the cryptographic mechanisms? Encryption. What is encryption? Encryption is orchestration of your data, so that you take your plain text data and garble it in such a fashion that only the recipient for which the data is intended for, only that particular entity or that particular individual will be able to decrypt or extract the meaningful information from that garbage, which looks garbage to the outside or the person in between. Now, signature, you also need to verify that your data, or whether your information which has been exchanged, it is coming from the intended party, so that the sender or the receiver should know that, okay, the information that I'm receiving is from the right source. It has not been tampered by anyone. Now, data authentication and hashing goes hand in hand. The concept is mutually similar, where it's being used in order to verify that my data or my information which is being exchanged, it has not got tampered. Somebody has not changed any text in it, like a piece of information, such that the current president is suffering from a terminal illness. This piece of information, if modified, that the acting president has been has demised. Okay, the two informations can be taken up in different manners and can have different impacts. The next two mechanisms are key establish and random number generation. So what is key establishment? So anything, all the algorithms that being used, it may be hashing algorithms or it may be encryption algorithms, they take a key establishment, or they need to use a key in order to, which is act as a feed in the algorithms. Okay, and who provides that random numbers is the random number generator. So you need to have, when you are developing a cryptographic system, you need to have a solid random number generator, such that it should be very large and it should be every time unique. It should not produce a pattern, because if it produces a pattern, that means it is easy for someone to guess. Moving ahead with, let's move ahead to our first topic, which is hashing. So hashes and HMAC. So what is a hash function? A hash function is a one-way function. It's an irreversible function where no matter what is the length of input that you feed to the function, the output is always of fixed length. It can be of size 128, it could be of size 192, 256, or 512 bits. But it may be a 1 gig of data that you're feeding it to the system or feeding it to the function. It may be a 10 gig of data, but the output is always going to remain of fixed length. What are the characteristics of a hash function? As you can see that it's avalanche, pre-image, or collision. So what each of the characteristics tells about the hash function is that no two messages should produce you the same hashing function. If two messages can produce the same hashing, it means that that's not a good hashing algorithm. It can be easily cracked because I can tamper the message and still produce the same hash. Pre-image resistance, as I said in the beginning, that hash is a one-way function. It's an irreversible function, which means that you cannot take the hash and reverse engineer to get the original message or the original effect. And the avalanche effect is that even if you make a small change in your input, it will have a big change in the output. So you can take a hash of 2 files, okay? Even if you change a small character in it, the output of the hash is going to be a big difference that you can see. Now, so I said that hashing is a one-way function and no two messages should be producing the same hash. So what are the hashing algorithms that is known to our audience? Can anyone say, or anyone can write up in the chat? What are the known hashing algorithms which are currently known? Shah, yeah. Thank you. Yeah, that's correct. So there has been a number of variants of SHA, as you said. Somebody wrote as SHA 5112. So there is SHA 1, SHA 256, SHA 5112. Okay. And previously there was something as MD5. Okay. Now you will see that, okay, I have a small demonstration. Okay. So let me slide over here. So in this, okay, we say that a hashing algorithm should be collision resistance, which means that two messages cannot produce the same hashing output. So if you see here on this folder, I have two images of two planets of our solar system. One is Mars and one is Venus. These are two independent images. Okay. Now, there is a small program which was written. So if and just to verify that I am in the directory where there is no other file except Mars and Venus. Now, when we run a small program on it, we created two PDF files, okay? Now, let's look at the content of the two PDF files. So one is Mars collision, which show me the planet Mars, and one is Venus collision, which show me only the image of our planet Venus. Now, let me calculate the hash of the original images. So OpenSSL SHA-1 of Mars. And let me also calculate the hashing of Venus. So we can see that the hashing, when I feed the images to the hashing function of SHA-1, okay, the output, the hashed output is completely different, okay, which tells me that, okay, SHA-1 is a good algorithm, as a good hashing algorithm, and it is not vulnerable to collision. It is collision resistant. But after running the script, okay, where I created two PDFs which shows the Mars and Venus, let me calculate the hashing on them. So Mars collision, and now if we see that the hashed output of both the feeds or both the inputs is same. So can we say that SHA-1 is completely collision resistance? No. SHA-1 is not collision resistant. There is a trick behind this PDF, but from this we can know that SHA-1 is not completely collision resistance. Some of the pre-computation before hashing is done, it can be extracted, which results for an attacker to be able to successfully do a collision attack. Now, this is not possible in real time, okay, when the keys are of short duration, the lifetime of the keys are of short duration. But think of certificates, okay, using certificates hashing as the SHA-1, okay, and they have a validity of, like, we have seen in real time, people have got certificates which are valid for 10 years, 15 years. This is not the right algorithm to use, because it gives you enough time for an attacker or for a mathematical researcher in order to find shortcuts or in order to find faults in your algorithm. So we have seen that how SHA-1 is not completely collision resistance. Moving ahead with that, let's see that what happens when we do hashing or HMAC. So in this representation, we see that there is the person Alice and there is an individual Bob, and they wanted to exchange a message, and they also want to validate that the message exchange is not tampered. So Alice formulates a message, okay, and pass that message through a hash function. And when she transfers the message, she transfers the message along with the calculated hash. Now, when Bob receives the message, he locally calculates the hash again on the received message and compare the locally generated hash output with the received hash output. If the locally computed value matches with the hash value that I have received, then Bob says that, okay, the message is valid. If it doesn't match, then Bob discards the message saying that it's an invalid message. Now, what's the difference that HMAC brings? So think of a period where Alice and Bob thought that, okay, let's have a shared secret, okay, exchange between them. So during peaceful hours, what they did is that they exchanged a key, a passphrase between them, that we will be using this passphrase, okay, when we'll be sending messages in the future, when there are critical times or when we have to send critical messages, we'll be using this key. So what happens in HMAC is that they have already shared a pre-shared key, okay, or a passphrase. They have this common passphrase between them. Now, when Alice is trying to send the message and trying to calculate the hash is not only calculated on the message, but also in combination with the key or the pre-shared key or the passphrase which has been exchanged and common between them. So now if we see The feed of the hash is the combination of the message along with the pre-shared key. The same thing happens is that Alice sends the message over the wire and along with the HMAC. And when Bob's receive it, Bob locally calculates an HMAC on the received message and compares the locally generated HMAC with the received HMAC. If the values matches, the message is valid. If the values doesn't match, the message is invalid and discarded. So with this, we know now that what are the feeds of hashing and what are the feeds for a HMAC. So let's look at what difference does it make when we introduce an attacker in each of the scenarios. In the case of hashing, okay, Alice is trying to send a message, the same message, and computes the hash on the message. Now, there is a attacker or there is a man in the middle named as Mallory who is sniffing the communication between Alice and Bob. So what Mallory does is that Mallory intercepts the communication, and since the message is in plain text, he takes the message, manipulates the message, and he creates a new message. And basically what he does is that he calculates the hash on the new message and forwards it to the Bob. Now, when Bob will receive the message, what will happen is that Bob just recomputes the hash on the received message along with the recomputes the hash and compares the locally generated hash with the received hash. And the same thing, that if it matches, it's a valid message. If it is not matching it, it's something which has to be discarded. Now, what happens in HMAC? Alice is again trying to send a message to Bob. And in this case, the hash is calculated using the message in combination with the pre-shared key, which has been exchanged between them. So when Alice is sending the message over the wire, Mallory can still see the message, can see the HMAC. Now, but if Mallory changes the message, okay, Mallory is unaware of the key which has been exchanged between them. Mallory can intercept the message and calculate a new hash. But will Bob be able to anytime consider that this message is valid? No. Why? The reason is that when Mallory will try to compute an HMAC, Mallory will guess a pre-shared key and will try to compute the hash. And that hash is never going to match, or that HMAC is never going to match when Bob computes the HMAC locally with a key which was previously shared between Alice and Bob. So even though Mallory is trying to intercept the message, but when Bob receives the message, the HMAC will never match, and every time the message will be discarded. So here, even though Mallory can sniff in the message and HMAC, Mallory will not be able to modify the message or recompute the hash because Mallory is unaware of the key which has been exchanged between them. Having said this, could people or could the audience tell that which one should be used, whether it should be hash or whether it should be HMAC? Thank you, Shobha. Thank you. I hope this presentation helped you understand that how hash can be manipulated, but how HMAC cannot be manipulated, even though there is a attacker or there is a sniffer in between the communication. With that, hashing and HMAC, okay. Now, let's look at what are some of the applications of hashing. So where all hashing is being implemented. So hashing is being implemented for passwords, for malware, and for verification of data. So how is it implemented in passwords? So we all have accounts in multiple websites, in multiple applications, okay? Like people have, the one definite is Facebook, that people have an account, Facebook, Gmail, LinkedIn, and there are multiple websites that we have our account. So what do you think that when we sign up an account, okay, on any web application or any application or on any website, how are the passwords being saved? Any guess? Yeah, right. So if you save the passwords in plain text, okay, it's possible for everyone to read it, as well as we should always think of the scenario that we, as an application developer or as a website developer, that I will be under continuous attack all the time. So how I can save my system? So when you sign up an account, okay, on any website or an application, you enter your password. So what exactly gets saved on your AAA or on your authentication database is the hash of that password. So that when the next time you try to log in, it takes the hash and try to match with the hash which is there on my authentication database. If the hashes matches, then yeah, the user has entered the right credentials. If the hash doesn't match, yeah, the credentials are invalid. It also protects you that at any point of time, okay, if your database system is compromised, okay, as we said, that hashing is a one-way function. So it is not possible for someone that he can just look at the hashes and can compute back what were the passwords of that user. It is also used in malware and data verification. So malware files, okay, or infected files, okay, they create something as the hashing of that particular file and feeds it to the system, so that any point of time, okay, this particular hashing is matched, my security system will be able to recognize it and will be able to block it. And it is also used for data verification. You can think, yeah, can you think of any other fields where hashing is being implemented? Authentication, yeah, right. That is where the passwords come. Any other field from passwords, malware, or data verification? Digital certificates, right? Digital certificates, your blockchaining, or your file path linking in your programs like C, C++, Python, hashes are being implemented. Now, what are the other applications of hashing? The other applications of hashing is static hashes. So what exactly is static hashes? So think of, so here I have taken the example of French fries, because no matter you eat the French fries in India or you eat the French fries in US, they always taste the same. At least in McDonald's, we see that the French fries taste the same or they look the same. Now, how static hashes comes into picture is that no matter at what duration or at what point of time you take the hash of that particular file, the output is always going to remain the same. Think of a scenario like the malware file, okay? Whether it has infected one system or it has infected multiple systems. And no matter you calculate the hash on a single system or you change the location of the file to some other place, the hash is always going to remain the same. So that is what is static hashes. Now, there is one more great concept or implementation of hashing is the rolling hash algorithm. I'm not going deep into this one. So this is mostly for research purpose. This is mostly used for malware researching. If you guys are interested, I'll be sharing this the slides. Okay, you can refer the link where, and you can get more deeper details about rolling hash algorithm. So rolling hash algorithm in Assist is used in order to identify the patterns of a malware between two particular malware and identifying to a family of malwares. So with this, okay, we will jump to the next mechanism under cryptography, and I hope you guys were clear now that how hashing and HMAC works and which is more secure, hashing or HMAC. Let's look at the next mechanism, which is the symmetric encryption. Okay, so in encryption, there are two types of systems. One is symmetric encryption system and one is asymmetric encryption system. So let's look at both the systems one by one. So in symmetric system, I'll take the same representation where I have Alice and Bob who are trying to exchange a message and they want it to be secure. So during peaceful time and when they had a chance, they were able to exchange a shared secret between them or a common passphrase between them. Now, when Alice has to send a message to Bob, what she does is that she takes the message, locks it with the key, and then send it across to Bob. Now, Bob uses the same key in order to unlock the message and identify what are the contents. So think it like in a real-time example, think it like our the lockers we buy at home. Okay. So there is a document inside that locker, and what they give you is that you have two keys. Okay, two individual has two keys, but the key are the same. Or think of like your the same simple example would be like think of the key to your apartment. So each family member has the same key, right? They don't have different key. In order to enter or in order to identify what's there in the house, everyone has to lock using the same key and they unlock the door using the same key. So that is why it is known as symmetric crypto system. Now, let's look at one of the algorithms, one of the encryption algorithms of symmetric crypto system. So we are not talking about DES, 3DES, because those are something which are vulnerable and they are easy to crack, but you will find users who are still using DES or 3DES. Most of the platforms, the industry platforms that you will see in today's date, you will see that DES algorithm has already been deprecated. You can no longer use DES, but 3DES, you will see that some of the systems still still gives you the option to use 3DES as the encryption algorithm. But since those are vulnerable or the strength of those algorithms are less, okay, it's advised in today's date that the system should be moved to AES. So what exactly is AES? AES, also known as Resendel's algorithm, okay, it has a block size of 128 bits. So what it takes is that no matter you feed how much amount of data or what is the length of your message, it converts it into 128-bit block size. If the length of the message is not 128 bits, we do padding so as to make it a 128-bit block size or a 16 bytes block size. Now, it's a symmetrical block cipher algorithm. It takes your plain text, converts it into 128-bit block sizes, and in combination with the key, okay, it could be a 128, 192, or 256-bit key, it produces your cipher text. Now, depending upon the size of the key, AES can have multiple rounds. It can be so 128-bit has a 10 round 192 has 12 rounds, and 256 has 14 rounds that the AES goes through in order to finally produce you a ciphertext. When I say ciphertext, it means converting my plain text information into a garbled information or an encrypted information. Now, it works on substitution and permutation. So there are 4 steps that it goes through. One is the substitution of your bytes, shifting of the rows, mixing of columns, and then adding it with a round key. So when I say the rounds, okay, as I said that there are different, or the number of rounds differ depending upon the size of the key that we are using. So every round will be using a different key. Now, in the slide itself, it was supposed to be a question, but everyone can see it in the slide that this is a 56-bit algorithm. That means any person, okay, who has to do a brute force attack against a ciphertext has to go through 2 to the power 56 number of operations in order to sweep across all the known keys with which my message could be encrypted. But if we look at AES, the key size is much large to accommodate your block size as well, which starts from 128. So it is said that if a 56-bit DES can be broken or can be cracked in 1 second, it would take a minimum of 149 trillion years to crack a 128-bit AES. Now, in the 192 space, we the number of keys is more than the number of atoms in the universe. That accommodates that. Now, how do we? So, as I said, okay, in order for an AES to crack, okay, if I'm using the key lengths of 128 or 192 or 256 bits, I have to do that many number of operations, 2 to the power 128 or 2 to the power of 192 or 256 operations against my ciphertext, okay, to fully or partially be able to run a brute force attack. So you can see that how what is a dramatic difference that a 128-bit key length can showcase. So the age of our universe is what, around 14 billion. And if we see that it will take 149 trillion years for a AES 128 to crack, unless there are mathematical advancements, mathematical research, which are able to find shortcuts. But if we have to only sweep through all the keys, it's going to take that much amount of time. And I think by that time, we may not be existing. So with the AES encryption, I have taken a visual representation of how these block ciphers work, or what are the mode of operations of each of the encryption algorithms. So there are 3 modes that you can see, is ECB, CBC, or counter mode. So if we look at the 3 results at the bottom, okay, so we can see that in the first one, the image is clearly visible. The second one, it's partially, and the third one, I do not know what's inside that. So our brain, okay, so why I have taken this visual representation is because our brain is very good sometimes in order to identify patterns, even after a tiring party or a late night sleep. When we see something visually, our brain tries to figure out what is the pattern behind it, or what could I see behind that, even though it is not clear. So what each of these modes, how each of these modes, okay, encrypt your data so that we can find a perfect encryption so that there should not be any pattern which is visible. Now, what happens in ECB mode is that I take the message, okay, I divide the message into blocks, and then I pass it through the encryption algorithm. It may be your DES, 3DES, AES, whatever algorithm that you are using. And I create the ciphertext. Whereas when we look at CBC, which is chain block cipher or counter mode, we take an initialization vector. So how this initialization vector, you have seen that we talked about random number generators. So that is what helps to generate an IV initialization vector. So we take the initialization vector, we XOR or we combine it with the first block and then pass it through the encryption algorithm. And then I get my first block of encrypted text. In order for be able to encrypt the second block, the output of the first block acts as the initialization vector for the second block. It's used in combination, and then it is passed again through the encryption algorithm. And finally, I get my complete ciphertext. Now here, if we see from ECB, we have broken the substitution, where ECB looks like a substitution. CBC is no longer like a substitution. I'm not trying to substitute my message to a ciphertext. Since I'm not trying to substitute, okay, it is difficult now to create a pattern. Now, the operation slightly differs in case of counter mode. So in this, the initialization vector is being selected, and then a series of that initialization vector is being created. So that IV1, IV plus 1, IV plus 2, 3, 4, and continuing. Now, we pass the IV instead of message, which was done in the CBC. I pass the IV through the encryption algorithm, and then I XOR the output with my original message. So I take the first IB, pass it through an encryption algorithm, gets the output, XOR it with the first block of my message, and creates the first block of my encrypted text. Now, similarly, this will continue, and a separate IV is being selected in each of the modes, okay, whenever there is an encryption that needs to be happening. Now, what is the drawback of CBC over counter mode? So you can see that, okay, in CBC, I have to wait for the encryption of my first block before I can encrypt my second block. Whereas in counter mode, the operation happens parallelly. So it's a parallel stream of operation. So I can encrypt each block parallelly. I don't have to wait for the previous or any input from the previous block. But what is the drawback? So if you see the last section where I'm combining the output of the encryption of the IV with my message, I guess you guys would be knowing something as one-time block or one-time pad. It is similar to that, just it depends upon the IV. Now the drawback of it is that you should have a strong random number generator so that the system never generates the same IV. It should be able to generate unique IVs every time. If a pattern is maintained, then and I can guess that, okay, after a period of time, this IV is going to be used, and now I can create a pattern that I can pad. I can use the one-time pad with the message, and it will be easy now. So that is one of the drawback. But in terms of operational speed, or in terms of operational speed, you will not find much difference unless your system or your implementation is very critical, where it checks for even the nanoseconds that or the picoseconds that, okay, there is a delay of any such thing. Now let's jump into the world of asymmetric crypto system. So we have looked into symmetric crypto system, what is a symmetric algorithm, and what are the modes in which a encryption algorithm works. Symmetric encryption algorithm works. Now look at something which is asymmetric crypto system. So why we call that as a symmetric crypto system is because we use the same key. Both the entities use the same key in order to either encrypt the data or in order to decrypt the data. So what happens in asymmetric crypto system? In asymmetric crypto system, when the sender has to send a message to the receiver, in this case, Alice is trying to send a message to Bob. So she encrypts the message using one key and pass the message to Bob. Now Bob has both the keys. Bob will use another key in order to decrypt that message. So think of your like bank lockers, okay? So in bank lockers, when a locker is assigned to an individual, there are two keys in order to open the lock, and both the keys are not the same keys. Similarly, in asymmetric crypto system, one key is used for encrypting or for locking the message, whereas the other key is used to unlock this. Now, how do we use that, or how do we extract or how do we calculate such keys, that one key will be used for encryption and the other key will be used for decryption, or one key will be used for locking whereas the other key will be used for unlocking? So in the year 1970s, okay, three mathematicians, you would have heard the short form of it like RSA. So Rivest, Shamir, Adelman, these are the three mathematicians who came up with the arithmetic equations, okay, or with the arithmetic algorithm using the base as modular arithmetic. So in asymmetric crypto system, the sender and receiver, the sender and the receiver will be using separate keys in order to encrypt or decrypt, and they will be doing different set of operations, but the base of those operations will be the modular arithmetic. So what is a modulo? Modulo is a clock. So if you feed a infinite series into a modulo, it's going to give you a finite group. So I go from 0 to infinity, but my modulo will always reset when it reaches to that specific number or whichever is the modulo. So in this case, we have taken an example of modulo 4. So 0. So 1 modulo 4 is 1, 2 modulo 4 is 2, 3 modulo 4 is 3, and 4 modulo 4 is 0. So every time I reaches to that number, my system resets. Now, they took that modular arithmetic and created an equation, okay, which can be used in order for the derivation of those keys, such that my asymmetric crypto system can be established. Now, what is the arithmetic equation that they devised, or the modular arithmetic equation which was taken? It is b to the power x mod n is r, where b is the base, x is your component, and b to the power x means you multiply b to the number of times of x. Now, having known the values of b, x, and n, it's very easy to calculate r, the value of r. But if I am unaware that, if I do not know one of the parameters, okay, Like if I do not know what is the value of B, or if I do not know what is the value of X, it makes it very difficult either to find the nth square or the x square of R mod n, which is my RSA problem, or it's very difficult to find my exponent, which is the discrete log problem. Or now, so as I said, okay, in asymmetric crypto system, okay, the operations will be different. The crypto key elements or the keys will be different between the sender and the receiver, but the arithmetic function which will be used will be the same, which is our modular arithmetic. Having said that, let's look at how it has been implemented in our public key crypto system. So what is the advantage, or what was the motive behind public key cryptography? So what are the drawbacks that a shared secret was having, so that now that I want that I should be having an asymmetric crypto system? So one of the drawbacks, if you think of, is that if you're trying to share a secret, okay, and you have a large group of devices or a large group of implementation, creating a secret key, a unique secret key for every individual is a tedious job, and it's a difficult job as well. It also increases your risk of getting compromised if you are maintaining a uniform key across all your system. So if one system is compromised for any reason, it's like compromising my entire infrastructure. What is the advantage of having the asymmetric crypto system? Is that now I have a public key and a private key, one for encryption, one for decryption. And these are mathematically computed values, which are practically impossible to crack. So what happens during a public key operation? Public key is something which can be distributed. It is supposed to be distributed, but private key is something that has to be always kept secret. The moment you compromise your private key, that means your system has been compromised. You have lost your identity, because now anything can be decrypted by using your private key. So anything which needs to be encrypted is used. The public key is being used to encrypt that information. So if you remember the slide where Alice was trying to send Bob a message, there were two color representation. One was the red and one was green. So red was the representation of the private key, and the green was the representation of your public key. So Alice was shared with the public key by Bob, and she used that key in order to encrypt the data. And how Bob uses in order now, whenever Bob is trying to send a message back to Alice, how Alice can know that, okay, it is Bob who is actually sending me the information and not some intermediate person. So the private key is used to sign the data. It is sometimes also referred as encrypting from the receiver side back to the sender side. And the public key is used to verify the signature. So in a Zest, public key can be shared. It is used to encrypt data, and it is used to verify the signature. Private key, which should be never been shared, it is used to decrypt the data, and it is used to sign your data. So we said that in asymmetric crypto system, they have different keys in order for encryption, decryption, for signing and verification, and all of them uses the base function of modular arithmetic. So what is the RSA algorithm? So how they develop this set of keys which can be used for encryption, decryption, signing, verify. So in RSA algorithm, we take two large prime numbers such as P and Q, and we calculate the modulus as P and Q. Now, as you can see in the slide, the totient of a totient value is calculated, which is nothing but the product of P minus 1 and Q minus 1. Having calculated these values, we derive two exponents. One is my public exponent E, and one is my private exponent D. Now, what is exactly a public key? A public key is a combination of the modulus and the public exponent, whereas the private key is the combination of your modulus and the private exponent calculated. Now, let's see how modular arithmetic is being used over here, okay, in order for each of the operations. So when a message or a plain text message has to be sent, in order to encrypt or in order to create a cipher text, we take the message and raise it to the public exponent modulus n. Similarly, while decrypting, the receiver takes the ciphered message, raise it to the power or raise it to the exponent of its private exponent modulus n. Signature and verification, again, the same thing, that when I have to sign the data, I'm taking the message, raising it to the private exponent, doing a modulus n, and while verifying, the receiver raise the signature to the exponent of the public exponent and do a modulus n. Now, what does modular arithmetic brought is that, so if we draw a graph, okay, and we check only the exponential graph, it will create a pattern, okay. But when we introduce modular in that, the pattern is now scattered. That is why modular arithmetic was being used for asymmetric crypto system. So I guess till this topic, we are familiar how RSA operations and how RSA algorithm works, and what keys can be derived and how keys can be derived using modular arithmetic, and how encryption, decryption, signing and verification is being done. So having said that, in asymmetric crypto system, what can be done by one key can only be done by the other key, or what can be undone by one key and only done by the other key. Like we saw, any message which can be encrypted using the public key can only be decrypted by the private key, so that none other than the person who holds the private key can decrypt the message. Any person who signs the message using the private key, it can be only verified by using the public key. Now, let's look at what are the components of our PKI infrastructure or our public key ecosystem. Like our universities, okay? So when a student registers in a college, he is registering a roll number or a registration ID is generated. And once he completes all the semesters, a certificate, a passing certificate or a graduating certificate is being provided by the university, satisfying that, okay, this person registered in this year and completed his education by this period, and we take the responsibility, or we acknowledge that this person has successfully graduated from such college. This is his name, this was his registration ID. Similarly, in PKI infrastructure, there are centralized and globally trusted bodies, okay, who are responsible for issuing certificates to entities or to organizations or anything. Now, along with that, the CA also provides you a mechanism that in case if anything is compromised, like I said that in the previous slides, that the private key is something that should be always kept as a secret. In such cases, if the private key is compromised, the CA should provide a mechanism where the person should be able, or the person to whom the certificate is being presented, he should be able to know that, okay, the certificate is a valid certificate. There has been no compromise which has been done. So how does a certificate structure looks like, or how does a certificate signing process works? So we take the certificate structure and pass it through a serialized function. And the output of the serialized function is passed through a one-way hash. And the output of the hash is signed using the RSA algorithm. And the signature of the CA is embedded with the issued certificate. So CA uses his private key to sign the hash which has been computed, and then we can see the CA signature in the issued certificate. So you can take any certificate which is available. Okay, you can download any certificate of any public domain, or if you have a certificate of your from your internal CA server, and you can just parse it through OpenSSL. So what all information that you will see is that what are the certificate properties, like what is the serial number of the certificate, from which date to which date it's valid from, then who is the issuer of that certificate, so that who has issued the certificate, whether it was your university, whether it was Kochi University, whether it was Karnataka University, or whether it is Bangalore University. So that any point of time, anybody wants to know that from which person the certificate has been issued, they can know about it. Along with that, there is a signature algorithm. And then comes the details about the certificate, that to whom the certificate has been issued, and what is its public key, and what this certificate can be used for. So there is an important field in the attributes of certificate known as EKU, or extended key usage, which tells that for what purpose this certificate can be used for, like whether it can be used for server authentication, it can be used for client authentication, it can be used for IPsec, it can be used for email, and various other purposes. So this is just a comic representation that what are the contents of a certificate if we compare it with our passport. Now, in the first slide of PKI infrastructure, I told that the CA should also provide you a mechanism in order to identify that the certificate is revoked or it has been compromised. Let's not hope that it happens with any of the students, but let's assume a scenario where the certificate was issued by the university, and at one point of time it was found that there has been some malpractice, or that certificate needs to be made null and void. Similarly, in case of PKI, the certificate authorities, they maintain a list, a centralized list, also called as certificate revocation list, which contains your information like what is the serial number, when was the certificate being revoked, what is the reason behind revoking that certificate. It may be the system was compromised, the system was thrown away, but it was not completely flashed. So we have in mind that, okay, my certificate may have been in that store, so I should revoke and I should get a new certificate. Now, or my private key is compromised. Somebody was able to get access to my system and was able to extract the private key. So in these conditions, the certification revocation list needs to be verified, okay, in order that I should know that the presented certificate, whether it's still valid or it has been revoked. Now, this file is updated periodically from time to time. And since it is signed using the private key of the certificate authority, which is only known to that organization or to that entity, it cannot be tampered with. Now, you could see in real time out of experience, we have seen um, that sometimes people use certificates, okay, where the certificates have gone invalid, either because of the validity period, the period has ended, or certificate has been revoked, but still the authentication works, or still I'm trusting that certificate. Now, why this happens? So when you are trusting a certificate which is being presented, okay, you need to validate that who is the issuer of that certificate. If I trust the issuer, I know that, okay, I trust the certificate, the identity certificate as well. But we sometimes the system doesn't look into a location which is where the CRL files are stored. It is known as the CDP point, which is embedded in your certificate. That whenever somebody tries to know about that, whether my certificate is still valid, go and look into this location, and you can download the CRL file and you can compare whether my serial number is listed or not. If that things doesn't happen, my certificate can, even though it is revoked, it can still be accepted because I'm not verifying it against the certificate revocation list. So as I was saying, that what are the contents of a certificate revocation list? The contents of the certificate is like who has issued the certificate. In this case, it will be the CA. Now, when was the update been done? As I said, it will be periodically updated. So when was the last update done and when was the next update going to happen? Then the list of serial numbers of the certificate, when was revoked and what was the reason behind it. Now, when you are using CRL revocation as a mechanism in order to validate your certificate, one thing to keep in mind is that not have a validity. I have seen people using CRL file which are valid for like months, years. In this period, what happens is that my system is not going to download the certificate CRL file every time, because I know that I have downloaded the CRL file now and it's valid for next 6 months or a year or 2 years. In between this period, if I am revoking any certificates or any certificates are being revoked by the CA, the system is not aware of it because it's not downloading the latest CRL file. Rather, it's waiting for the next time period when the update is going to happen so that it will download the updated CRL. So always keep the CRL file validity shorter, not too short, but not too large as well. This is the same thing where I'm showing just 2 certificates. And lastly, as I said, that every file which is being maintained by the CA will have its signature so that it cannot be tampered. Now, let's understand the PK hierarchy. So I'll take the same example of issuing certificates from universities. So a student, so when I got the job, okay, I had my results published, but I don't have my certificate so that I can present it in my organization when I was joining. Similarly, your university gives authority to the colleges, okay, that the colleges can present you, the colleges has the authority to give you a certificate saying that, okay, the student with such serial number, name, branch and all have passed from my college from such university, and this is the course period of. So that acts as a validation. When I present that certificate in the organization, my organization can contact back to the CA or the issuer, who is my college, and can validate my details, that whether I have studied, whether I have passed or I have failed or something like this. So I can, in PK as well, there are something which are root certificate authorities and which are subordinate certificate authorities. Like in this example, the college was the subordinate certificate authority and my university was the root certificate authority. So my hierarchy can be in such fashion that I can get a certificate from subordinate certificate authority who has got its certificate from the root CA, or I can directly contact my root CA to issue me a certificate. And this hierarchy is uh, not limited to the slide, okay, that I'm showing only one subordinate authorities. You will find that there will be what to say, there can be multiple subordinate authorities, like the uh, root certificate authority designated one subordinate that, okay, you can issue certificates. Then that subordinate authority designated another subordinate authority that, yeah, you can also issue certificates. So this hierarchy is not like a 2-level hierarchy. It can be a 3-level hierarchy, or if you want to build a 4-level hierarchy, you can build some. Now, let's look at one more implementation of modular arithmetic. So in our previous example, okay, during symmetric encryption system, we saw that Alice and Bob used to share a secret, okay, ahead of time, so that during the time of need, they can use that particular shared secret in order to encrypt their message and pass across each other. Now, think that it's not now feasible in order to pass the message like handwritten, or I cannot mail it to you. Alice is in Earth and Bob is in Moon or Mars or anywhere, and they need to establish a secure communication, but they also need to derive the keys. So what happens in Diffie-Hellman is that Bob and Alice, they agree upon a DH parameters that they will be using, or they negotiate it, like in terms of IPsec or AICTE, you would see that they negotiate that what is the Diffie-Hellman group that we both are going to use. Now, if you look into the RFC, okay, you will find that for any particular group, what will be the generator, what will be the modulus. But when Alice and Bob is trying to exchange this information, what they do is that they choose another random number and they use the modular arithmetic to compute a public key, which is APUB. APUB is G exponent A mod P. And when it is sent, Alice is sharing the public key, which is the generator and which is the modulus, which can be easily found from the RFC as well. But what she doesn't share is the random number which is selected by her. Similarly, when Bob receives, what Bob does is that Bob also uses, because they have agreed upon using the same generator and modulus, Bob chooses a random number as B and creates a public value as BPub. Now, APUB and BPub is being exchanged between them. The attacker can look into that, which is the generator being used, which is the modulus being used, and what is APUB and GPUB. But since the attacker is unaware, okay, or we reach to our log discrete problem, he will not be able to compute A and B. And the beauty of this is that when they calculate the secret, okay, after with the combination of, or with the exchange of APUB and GPUB, it creates a common secret, which is represented in the below section, which is GAB mod P, or it can be like GBA mod P. Now, Diffie-Hellman itself doesn't provide. So let's see that when an attacker comes into in the scenario. So in this case, we saw that if an attacker knows about APUB and BPUB, he will not be able to generate the secret because he is unaware of the random numbers A and B. But the attacker can impersonate himself as Bob to Alice and Alice to Bob, so that When Alice is sending a pub, it's held by Mallory, and Mallory sends mpub back to Alice. And when Mallory is interacting with Bob, okay, he takes bpub and interact and shares mpub. So that now, since Mallory is the person who is impersonating as Bob to Alice and Alice to Bob, okay, he got the public values from both and used his or shared his public value with both of them. Now he can have a secret which is common between Alice and Mallory and between Mallory and Bob. My system is broken. Now, DH itself doesn't provide you protection. Okay, it provides you a mechanism to share a key or to generate a key which is passed as an input or feed to your cryptographic algorithms in order to derive session keys, but it itself doesn't provide you the protection. That is why, along with DH, okay, almost like all the systems, they go through the steps of, it may be TLS, it may be IPsec, it may be any protocol, okay, it may be SSH. They go through all of these fundamentals of like, what will be my generator and modulus that we'll be using. We'll exchange our DH public values, which is a pub, b pub, or sender pub, receiver pub public values. And I'll also authenticate from whom I'm receiving the message. So even though Mallory says that, okay, I am Bob to Alice, but when we are authenticating, Alice will be able to know that, okay, this is not Bob whom I'm talking to, or Bob can know that this is not Alice who I'm talking to. So I'll discard the communication. So with this, okay, you will be able to now understand the RFCs and the functions. It may be any RFC regarding TLS, or it may be related to IPsec. You will be able to understand that what happens, because the base remains the same. I agree upon the generator modulus, we'll exchange DH values, and then we'll derive the session keys. Now, I'll be going a little fast on these sections because I guess you guys already know about it. So so on the browser, in real-time scenarios on browser, you'll see that when you go to a particular website, it says either not secure, or so it will say not secure when you're using HTTP, even though when you use sometimes HTTPS, and it says that the website is still not secure because the certificate is invalid. The certificate can be invalid due to multiple reasons, like the common name doesn't match, the validity period has expired, the certificate has been revoked. And in case where the certificate is valid, like the common name matches, it's issued by a proper CA, the certificate has not been revoked, and then you see a green lock icon on your browsers. So what's basically SSL? SSL is a handshake that is being done between a client and server. What things being exchanged, like the version, the cipher suites. The cipher suites include what is the protocol that is going to be used, what is the encryption algorithm that's going to be used, and what is the key exchange algorithm that can be used. Like it can be RSA or it can be DH. So what happens between RSA and DH exchange is that in RSA handshake, a pre-master secret is being calculated between the client and server, and that is being exchanged by the client by encrypting it with the public key, and by the server by encrypting it with the private key. But what happens in DH is that private key is calculated, which is kept secret by the client and server, and they exchange only the public values, which are further fed into a system in order to derive the session keys. So if you look during the handshake, it's an asymmetry because we are using different keys in order to encrypt and decrypt. But once the session is being established, it will be using the same keys which have been derived, and it becomes a symmetric system. TLS 1.2 handshake versus TLS 1.3 handshake is that in TLS 1.2 handshake, there are 6 messages which are being exchanged to and fro between client and server, whereas in TLS 1.3, only 3 messages are exchanged in order to complete the handshake process. Now, TLS 1. In TLS 1.2, the first 2 messages are not encrypted because till that point of time, we have not been able to derive any kind of keys. But in TLS 1.3, it is more secure because starting from the second message itself, okay, everything is being encrypted, or starting from the very beginning, everything is being encrypted. That is why it is more secure. That is what is being represented in this slide, is that TLS 1.2, 1.3. So one is RSA. TLS 1.2 supports both RSA and DH, whereas TLS 1.3 only supports DH, so that any point of time, if my private key is compromised, I'll still not be able to decrypt a TLS 1.3 session. Whereas if in TLS 1.2, if I'm using RSA key exchange, my private key gets compromised, I'll be able to decrypt all the previous communications or previous sessions. It is not 1.2 supports weak ciphers, 1.3 doesn't support. As we saw that the number of communications is less in 1.3, and in TLS 1.3 is not susceptible for downgrade kind of attacks. Now, to conclude our journey in Cryptoland and our session. So a key strength. So how do we measure key strength? So a key strength is measured depending upon the number of operations that a system has to go through in order to implement a brute force attack on a ciphertext. Now, in the year 1990s, a 64-bit crypto system was considered to be stronger, but in today's period, it is not anymore because of multiple reasons. So at least in order to have a stronger key strength, 96-bit key size should be used. 128 creates a dramatic impact because it takes 2 to the power 28 number of operations or operations in order to pass through all the sweep through all the keys before I can do a partial or full complete brute force attack on a system, or I can partially or fully break a system. Why do we need to increase the key strength day by day? With the advancement of time, okay, not only so with the advancement of time, what happened is that not only the attackers gain more strength. So previously there were less number of the systems were not that capable. Now the systems are capable. Even a home computer is such strong. It can handle so many operations, and now you have the option to even rent a platform from any cloud vendor, and you can run an attack. So the CPU resources increased. Not only the CPU resources increased, as I said, that you should always consider that you will be under attack. Mathematical advancements happen, mathematical research happen, which were able to find shortcuts in my algorithm, such that if my key strength is 2 to the power is 96 bits, where I have to run 2 to the power 96 operations, mathematical advances found shortcuts where I don't have to run that many operations in order to run a successful brute force attack. So algorithms never get stronger. So as I said, not only the CPU resources increased, but mathematical advancement, which added the shortcuts to my algorithms. And now with a change in time, okay, whatever the key strength which was considered to be strong yesterday, it may not be considered in future years or today. So every time the algorithms are getting weakened and weakened. Now, as much mathematical research is done with regards to that algorithm, or the CPU resources or the power of running the operations increase. So we cannot remain static. So my systems cannot remain static. Industries have to go through update from time to time. When we see that things are turning sour, that something can be cracked, now it's time to go to the next. Now it's time for me to upgrade. So things can never remain as static. So we move from AES to 3 days, from 3 days to AES, from from AES to RSA, RSA to elliptic curves to post-quantum computation or post-quantum algorithms. So what is the current what is the current signature hashing or encryption algorithms that you will be finding in today's date? We found a major of the population has moved to AES 128 CBC mode, but we see a large population still using DH of 1024, RSA of 1024, and SHA-1. So as we have seen through the demo that collision attack can be done on SHA-1 successfully. We should not be using DH1024. It's fine to use 1024 where the lifetime is small, like in the case of IPsec. But in case of certificates where my lifetime is in number of years, like 10 years, 20 years, 30 years, we should be moving ahead. We should not be using smaller key size algorithms. And one more thing is that we should not be having certificates with that large validity period as well. So what is the next generation encryption, or what is said to be ideal or suggested is to move to at least to 128-bit key strength. So either use 128 AES cipher or 256 signing cipher, signature, or hashing. Now, these are the next level of ciphers or next level of algorithms that are being suggested. Now, industries like defense or industries like capitalization, banking sectors, they want their systems to be completely secure. They want their systems to, they want the secret to be held secret for a longer period of time. So in those cases, these are the list of algorithms that should be used, which is good for a long period of time, at least for the next 30 years. These are good. So with this, I reach to the end of my presentation. I hope this presentation was helpful to you guys. It was I hope I was able to clear out the concepts of cryptography, and you enjoyed my session. Thank you.
Participants, if there are some questions, kindly type in the chat window. I can read it for Mritunjay. Mritunjay, there is a question. Can the CRL itself can be edited or tampered with?
The CRL cannot be, so you can edit the CRL, but so when you get a certificate, on the certificate, there is a CDP location, which tells you that where is your CRL file located. Now, anybody can download the CRL file. I can edit the CRL file, but the CRL file is signed by the CA. So if I if I tamper the CRL file, I'll not be able to match the signature because I have to sign it with a different private key. So in that case, even though my client will be able to download that CRL file, but it will not validate because the signature will not match. So in a nutshell, the CRL file cannot be tampered. I hope that answers your question.
There is another one, like, can you kindly brief about AES GCM?
So I have not included that in this particular slide due to the time constraint. But AES GCM is kind of a symmetric algorithm. It is much faster, and there it needs actually a little bit of explanation how it goes through. It takes the IV, it goes through each round in order to produce your ciphertext. So if you want about it, what I can do is that I can include that in the slides that I'm going to share, and you can connect with me sometime so that I can have a detailed explanation about that particular.
Thank you. Any more questions? Maybe you can type in the chat window. So thank you, Mritunjay, for a wonderful lecture. It was indeed a primer on cryptography, starting with the hash functions and then the algorithms, then certificates, and talking about the strength of the algorithms towards the end and what can be applied. So indeed, it was a learning lesson for each of us. We look for future collaborations. We definitely will reach out to you. So on behalf of the Department of Computer Applications, Cochin University of Science and Technology, and all participants present over here, sincerely thank you for your effort. Thanks, and we will meet again. Thank you so much, Mritunjay.
Thank you, Vinod sir. Thanks for giving me the opportunity, and I hope everyone would have enjoyed the session. Thank you.
Yeah, it was really good. Thank you.
Thank you. Bye-bye.
Bye. Which is something to be important, where we talk about the positive aspects of pandemic, and then we can take the exam, and the exam will be roughly about what we have studied from day one until the last. Okay, the slides will be shared definitely today with you all, but we are, if you see the chat on WhatsApp, we are sharing the videos. Okay, the session, the questions will be entirely based on what we have learned. It would be thoroughly based on what we have learned across the day one until what we learned today. So you will have to basically go through the videos, or maybe the slides that we share. Okay, it would be simple, but you just have to go through it. Okay, it is not that difficult. You need not worry. Okay, so maybe I would request each one of you to turn on the video so that we can have a picture. Maybe you can ping your friends if they're there. Maybe I can ping on WhatsApp, maybe. We'll just wait for a few moments. Maybe others are getting ready. Requesting participants to turn on the video if possible, please. It would be nice of you, like, since we are remotely joined, at least we expect one picture, at least at the end of the day, to retain the memory of this workshop. So in the call of 3, 1, 2, and 3. One more, just wait. Let me see the second panel. 1, 2, and 3. Another one. 1, 2, and 3. Okay, thank you for joining us, and we meet by 1:15 for a lecture by Dr. Ajit, which would be a generic lecture, and then we will close. Since people are joining, I'll again take. Okay. So then we can, we'll close the workshop, and you can take the exam on their ease. Yeah, so we have scheduled the examination that you can take it on your ease before 8 p.m. I feel that is how we have scheduled the Google form, because most of the people are working, they might be traveling, so it would be entirely an objective exam. So you have to, again I'm saying, you have to refer to what we have learned from day 1 until the last session. Okay, and it would be rather very simple. Okay. Okay, thank you. So we break for the lunch. Thank you. Thanks for joining.